So this is more or less my PhD work that I present to you today, which I did in Switzerland at Fiebel, together with also INRAE in France, in the context of the REMIX project, which was a big European research project on mixed cropping and advancing mixed cropping. So first an introduction. So I don't have to dig too deep into that. So mixed cropping is something that is often associated with the principles of agroecology, and agroecology are a whole comprise a whole set of principles, and one or the central principles of agroecology is synergies. Using synergies because in nature there are a lot of synergies, in ecology there are a lot of synergies, and so it's coming more from a perspective of taking advantage of synergies that are there in nature instead of imposing, so to say, our will on ecology, which is the more dominant paradigm in current agriculture. But agriculture tries to shift towards a paradigm that is more focused on synergies. So mixed cropping is very much connected to agroecology. It's basically an agroecological technique. I don't have to go into the details of these examples here. My previous speakers here have talked a lot about these. So we see here corn, soybean mixtures, wheat, faba bean, linseed, soybean, barley, and pea. And I've coined this as mixed cropping here, but it's maybe more agroforestry. But this is tomato, coffee, which also is a intercropping system. I'm curious if who can tell me what's the picture on the right shows. It's also an intercropping system. Three sisters. It's the two sisters. So it's just three sisters minus pumpkin. So it's maize climbing bean. Yes, it's maize climbing bean. And I've put this picture into there to illustrate why breeding for mixed cropping actually is important, because what you can see here are two different maize genotypes combined with the same climbing bean genotype. So, and you can see what happened here, and you can see what happened there. So this is a maize cultivar which has a very low lodging resistance, very unstable stalks, and it just crushed under the weight of the climbing beans. So just as an example for why genetics matter in the context of mixed cropping, and I, in my talk, will focus on pea barley as an example of mixed cropping. Why pea barley? Pea barley is, in Switzerland, where I did my PhD, a very established mixed cropping system, at least in organic agriculture, which is quite large in Switzerland. It's, I think, 12% of agricultural area is organic agriculture in Switzerland. And in the rotations of organic arable farmers in Switzerland, pea barley mixtures play an important role. It's a success story because the circumstances were right for the systems. As Peter already said, it has a lot to do with funding or with subsidy schemes, because farmers, as we've heard several times, they are very reluctant for complexity, so they tend to choose simple systems. So if there's not an incentive to go for more complex systems like mixed cropping, they won't do it. But there were two things in place here. So in Switzerland that favored this development. First thing, farmers got subsidies for barley pea mixed cropping because it counted as leguminous crops in the rotation, and they got subsidies for growing more legumes. So they could touch on these subsidies. And the second important thing is that there was a value chain put in place for it. So what that means, the main use of pea barley, these mixtures, is for the fodder industry. So they go for pigs, they are used as pig feed or as poultry feed. So the feeding mills, they have installed these separation chains where farmers could bring their mixed good like this, fully mixed, and they have these sieves and everything that separate then into pea and into barley. And this allows for the feeding mills to create specific feed mixtures that have a defined protein content and everything, because they want a defined product. They don't want to have any variation. They want to do the mixtures themselves. And once this was put in place, this created a market for farmers actually to sell their goods to, if they didn't use it on their farm themselves. But many farmers want to sell it to an exterior party, and this led to the success of this system. So we thought it's a good idea to use this established system as a model system for doing our research into breeding. And the research questions in this case were, do we actually need specific breeding for mixed cropping when using pea barley as a model system? If yes, what are the breeding related parameters such as traits, heritabilities, and genetic variances in such a mixed crop? And third, what is the prospect of breeding superior pea genotypes for mixed cropping? I put pea in brackets here because I'm mainly focused on pea in my project, not so much on barley. So these were the research questions, and what we did is we combined 27 pea genotypes with 7 barley genotypes to create different mixtures. Am I standing in front of you? So I get more here. This is better. We've only used registered European cultivars as for peas and for barley. For pea, we used spring types, and for barley, we used 2-row spring types. So this were spring sown, mixed crop. The peas were chosen to cover a maximum of morphological diversity, stem length, early vigor, and leaf type. I'll tell you more on the different leaf types in a moment. And 4 additional, so to say, genotypes were created by doing cultivar mixtures. That means cultivar blends containing at least 5 of these 27 pea cultivars, to also see what happens if we increase genetic diversity within one of the components of the mixtures. For barley, I chose these 7 genotypes to represent a gradient from very competitive to less competitive morphology in terms of plant height and leaf area, because we thought that competition between the 2 components will play a big role in the dynamics between these 2 crops. And I've also created 1 barley cultivar mixture, same as for pea, which was a blend made from all the 7 barley genotypes. Then a little bit of background into pea morphology, because actually pea is a very interesting crop in terms of traits. It's a very diverse crop. So here on the left side, just to illustrate, this is a pea plant with a stem with some side branches. Here you see the pods. Centered around the stem, you have these kind of leaves that are called stipules. And then you have the branches. And the branches, they can have different morphological forms. I'll show you in the next slide. But for the moment, bear with me, because here I also want to show you something about plasticity. So here on the top row, you can see the stipules of one genotype, and here the stipules of another genotype. The small leaves are always in mixture. So this is like the competition effect you see on barley on this plant. It has, you see also the plasticity that is present in this crop. You can also see, it's a bit hard to see, but actually there are also genetic differences in this, the size of these stipules. This genotype here has a bit more tinier leaves than this one, but I'll show you more on that later. Then leaf morphology. All these are side branches of peas, and this is like the morphology of these leaves is determined by 2 loci in the genome. And depending on the genotype, so this is the dominant allele, and in small letters, this is the recessive allele. But depending on the genotype of these two loci, you end up with these 4 different morphological types, morphotypes of peas. So you have here the leafy type, which is actually the wild type, like the most common type in nature. You have a tendrilless type. You see here these tendrils. So this one is missing these tendrils that help peas standing upright by clinging to other plants. You have a semi-leafless or aphylla type called sometimes. So here all these leaflets are developed into tendrils. These plants only have stipules around the stem, but they don't have these leaflets on the side branches. And then you still have this type here, which is quite particular. So you don't have these leaflets, but you have like these very tiny leaflets at the tips of the tendrils. Large morphological diversity, which is always very interesting for plant breeders. As a plant breeder, I love this. So in my PhD, I focused on the 2 main commercially available and relevant types, which is the wild type, this so-called leafy type, and the semi-leafless type. Commercially, this is the most used type, and the reason being that these plants, they grow into each other and they form a very stable canopy which doesn't lodge. So these types here, once they're grown and once their pods are filling, they're becoming heavy, they're tipping over, and everything is basically lodging if you don't have a tutor plant associated to it. So for the rest of the talk, like these are the 2 morphotypes we'll be talking about. More from pea morphology, like I've taken pictures of different peas that I used in my study, and you see like this large genetic variation for plant length on this picture, like with this very tall type here and rather small types here. For barley, it's a different story in terms of diversity. Like we have a bit of diversity in terms of plant length, like with this being the 2 outmost extreme types with rather large, rather tall stems and rather short stems, but this is it basically. So in barley, there's not so much genetic variation. So in this sense, it was also a good choice to focus on pea. I have to say this is also the reason being is that the genetic diversity in commercial barley material is very small because it's all brewing barley, and malting industry is the industry with the highest expectations in terms of quality. So this narrows down the genetic diversity in the commercial cultivars very much because they meet very defined qualities, and breeders are very reluctant to step aside from the material that works well in this system. And as for the methodology, like the experimental design, and Peter already nicely introduced this before, like if we were to use these 28 plus 4 P genotypes times 8 barleys, like the 7 plus the 1 blend, you would end up in 256 possible combinations. And these are simply too many. So like times, if you want to have 1 replicate, you are at 512 plots at 1 location, then you only have 1 location. Imagine it's a horror to measure all of this. So you need to come up, if you want to do genetic studies and with a more diverse set of genotypes, you need to come up with ideas. How do we cope with these exploding numbers of possible combinations? So we developed an incomplete factorial design. So that means that not every combination is present. Only 1/4 of all possible combinations has been tested. And this significantly reduced the experimental effort while little to no loss in precision of the estimated values. We could estimate the genetic values for yields, etc., with a mixed model. Here you see, just as an illustration, you see here the 8 barley genotypes, and here the 32 P genotypes, like 28 plus 4 mixtures. And every X here represents one mixture that we actually have been using. So they were randomly chosen, but in a balanced manner, so that one barley was always combined with 8 peas and one pea was always combined with 2 barleys. Yes, there's a question.
Yeah, you mentioned that you have little to no loss in precision.
Yes.
How did you actually know that?
Because we did simulation studies. So
yeah,
we did simulation studies. Peter has shown this already a bit in his picture, and I've published the principles of this simulation study in this paper here.
It's of course based on assumption.
It's based on assumptions. Yes. There's another question.
Yeah, also you're probably doing the assumption that GMA is more important than CA.
Yes.
Or maybe it's just one part of the experiment. Test more the candidates you selected.
This was an assumption, but we also tested in our simulation different scenarios. Also one that includes SMA, and also for that the estimates were quite precise. GMA, SMA, these are the pros here. Nicola works a lot with that. I'll explain what that means in a moment. The sowing pattern was fully mixed, like you can see here, this is like harvested good, but what you sow also looks like that. It's a blend of pea and barley kernels. And if you have the sowing rows in the fields, like with a farmer just sows it with a standard sowing machine with 12.5 centimeters row distance, and you have just barley kernels and pea kernels dispersed randomly into one row. So you get the full mixture as it's just different to strip cropping, of course. Yeah. The experimental setup was like this. We had it was a plot trial with 7 square meter microplots. As I said, the mixtures were sown as an incomplete factorial plus all the pure stands of pea and barley. So of every cultivar, we also sown the pure stand next to it. So what you can see here is one location with 2 replicates. This is the first replicate. This is the second replicate. And the more bright spaces, these are barley pure stands. So you can see nicely here where the barley was standing. All the more darker plots, these were either mixtures of pea plots. 2 replications, 2 locations in Switzerland with rather different soils. Uster with more nitrogen availability, Wieslisbach with less, in 2 years, and under organic management. The mixtures were 40% and 80% of the recommended pea and barley and pea sowing densities respectively. This is based on the extension service of Fiebel, which has found out with farmers over a long time that this is like the ideal sowing ratio. In terms of plant measurements that we did, you can see here a list. I won't go into the details, but we scored things like early vigor, total biomass, lodging, and of course grain yield. And grain yield, we measured the total grain yield, but we could also split these mixed grain yield into the pea component and the barley component, which is a very interesting detail I'll talk about in a moment. Some impressions, like this would be the measurement of the stipule length of the pea plants. And here on the right, on figure 2, you can see the lodging assessment with one pea genotype which has the worst lodging score and the other one next to it with the best lodging score. So big differences also when it comes to this trait. Now, like the models that we used to analyze this data. So this is the simple model for one location with Y being the grain yield, total grain yield, pea and barley mixed, mu the grad mean, and R the block effect. GB and GP mean the general mixing abilities of barley and pea, and I need to explain to you what that means. So the general mixing ability of a cultivar is its relative positive or negative contribution to the average yield of a mixture. So if you have for instance, if you have a very competitive and low yielding pea cultivar, this will end up in a negative general mixing ability because it has a low yield in itself, and it also is competing against the barley a lot, so the general mixing yield will be very low. It has a low general mixing ability. Next to that, we have also the specific mixing ability, which is basically the interaction effect of P cultivar A with barley cultivar B. So if you combine these two, you will have possibly a positive or negative effect based on the specific combination and the error term. What's important in the context of breeding for mixed cropping are these variances. So this is sigma G, and this is the variance of the GMA and the variance of the SMA. So if we have large effects of these main effects of these general mixing abilities compared to the specific mixing abilities, this will have a difference with regards to what breeding strategy you will apply afterwards. Because if you have a large and predictable general mixing ability in one crop, you can breed this specific crop regardless of what other genotype you combine it with. If, however, the specific mixing ability is large, it always depends on the other genotype that you're combining it to. Like if you combine PA with barley B or with barley C, will lead to a different outcome. So you need to test every individual combination. So, and this has implications for your breeding strategy. So it was important for us to assess these two variances, like the size of this variance with regard to the size of this variance. As I said, what we could do is we could separate this total yield here with a separation machine, so that we ended up having of one bag of these 7 square meter plots, we would have one bag of peas and one bag of barley afterwards. And this opened up interesting analysis pathway, because then you can split actually the genetic effect of one barley genotype into the effect it has on itself, which we called the producer effect. It's also sometimes referred to as the direct genetic effects. I think, Peter, you refer to it as the direct genetic effect, but it's the same. Or this barley genotype has on its companion, on the P, which is the associate effect or the indirect genetic effects. So direct or indirect effect of this barley on its own yield or on the yield of the P. Same for the P. It also has a producer and an associate effect. And if you combine the producer effect of P with its associate effect, it adds up mathematically to its general mixing ability. Here we go again. So you can split the general mixing ability into its producer effect and its associate effect. Same for barley, of course. So the model then for the partial yield looks a bit different than the one for, I skip back. So this is the model for total yield, Y, and this would then be the model for partial yield. And you see it just changes here, like general mixing ability of barley becomes associate effect of barley, general mixing ability of P becomes the producer effect of P. So this is then what adds up to the P yield, P fraction yield in the mixture. Do not fash. This is the full model, but it looks very complicated, but it actually is not so complicated, because we see again here the general mixing ability of P and of barley and the specific mixing ability. Here we see the block effect, location effect, the year effect, location effect, and the block effect, and the rest is just two-way interactions and the error term. And the full model for the partial yield here for P looks like this. It's basically the same. And this is, I won't go into the detail of this, but it's just the model of how we calculated heritability. I also came up with a suggestion on how you could actually categorize traits as for their biological interaction function. So I'll explain you what that means. So if you look at these scatter plots here, and you imagine that every time on the x-axis there are trait values, for example, plant length. So x is always plant length, and y is always, depending on what column you look at, is either the full mixture yield, the partial mixture yield of P, or the partial mixture yield of barley. And then plant length will have either, plant length of P will either have a positive effect, a neutral effect, or a negative effect on general mixture yield, positive effect on P yield, neutral effect on barley yield, or on barley yield, yes. And then this would be an ecology, this would be commensalism. And so you have these all these different ecological interactions here based on trait values and their effect on the mixture yield. You can basically categorize it by that. So this is how we approach this, and then this is what we found out. So just some basic raw results first. So these were the two locations, Wieslisbach and Uster, in the 2 years. Overall, we got a land equivalent ratio of 9%. So a 9% yield advantage in the mixture as compared to the pure stance overall across all the locations. You see that the means, they are between 3.7 tons per hectare total mixture yields up until 4.2 tons per hectare in total yield. But you see also interesting shifts in proportions depending on the year and the location. And I'm curious if someone can explain me why we have so much more barley in Uster as compared to Wieslisbach. Does somebody have an explanation for that? Sabine?
I guess it's drier in Uster.
No, it's actually not.
It's not?
No, no.
There's more nitrogen.
Yes.
Yeah, you mentioned nitrogen.
I mentioned it already. So it's actually relatively simple. Once you have more nitrogen, barley just becomes more competitive. It can take advantage better of the nitrogen, and this is also being reflected in our results here. Then I had a look, as I told you, I was interested into these variances between specific mixing ability and general mixing ability. So I calculated the variance components for P fraction yield, barley fraction yield, and total yield. And everything that is purple is an effect on P on the relative yield. Everything that is green is an effect of barley on the specific yield. And what you can see here is that I'm sorry, this is actually wrong. So this should go to this over here. So I skip that and I'll explain you orally. So again, if you look at P fraction yield, so the purple one here, this would be the effect of P on P itself, so the producer effect. And the green one would be the effect of barley on P, so the associate effect of barley on P. And likewise here for barley fraction yield. And you can see that actually brown would be the interaction between P and barley, so SMA, and it's actually absent, which is interesting news when it comes to our breeding strategy, because that means that general mixing ability is dominant, the main effect of cultivars in our specific setup. The heritabilities, they range from rather low for P fraction yield, 0.37. Actually, should I explain what heritability is? Maybe I should. It's not all breeders here. So heritability ranges from 0 to 1. And if heritability is 0, then the whole phenotype is purely determined by the environment. There's no genetic effect. If heritability is 1, it's purely determined by the genotype and no environmental effect. So in usually, especially with polygenic traits, we're ranging somewhere between 0 and 1. So the higher the heritability for a trait, the happier the breeder, because this means that the breeder has genetic leverage to change the trait. The lower, the less leverage a breeder has. So we have heritabilities ranging from 0.37 to up until 0.75. And for total yield, we have a heritability from 0.59, which is a moderate heritability. Yes.
How do you calculate your heritability? Do you take into account IgE in the response? Because if it's not exactly heritability, but the total heritable variance, and it's not limited to one.
I actually adapted this formula from Schmidt et al. To my specific case.
So it includes the GMA directly in this.
Yes, it includes GMA and SMA in the nominator, and here the error and the other terms in the denominator. It's also it's in the 2023 paper of my PhD. Does this answer your question? Sorry.
Yeah, no, it's just because it's kind of hard to just figure out how to calculate heritability in the interacting cropping system, because you have the phenotypic variance.
Yeah.
It's hard to define when you have multiple species at the same time.
Mm-hmm.
If you're looking to yield and you can have a mixed trait for both species, it's kind of easy. But when you have different traits for different species in the same environment, the phenotypic variance it's kind of easier to define. It's not that easy to define, but here I think
Mm-hmm. Yes, well, we had these separated yields, the yield fractions, and we had a multi-environment trial with replication, so it was actually possible to determine it. We also see a high heritability in the barley fraction yield, like this 0.75, and this actually is due to the leaf type. So what I mentioned before, these leafy types, they are lodging, they're strongly lodging, and so what you have here is a strong competitive effect of these types that leads to a lot of variance in the data. Like you have these genotypes that basically are profiting from for itself, but they're suppressing the barley, and this leads to this rather high variance here, so and heritability. When it comes to the question whether or not we actually need breeding for mixed cropping, or can we just use the best performing cultivars from pure stand for mixed cropping? I found these results here, like you see the P pure stand yield on the x-axis plotted against the total mixture yield here on top, and the P fraction here on the bottom in triangles. And like for total mixture yield, P pure stand yield predicts the total mixture yield with a correlation of 0.52, like a moderate correlation, but significant. Oh, it's not significant, but it is significant if you use only the semi-leafless, which are the black dots here. Which means, like, if we restrict us to the semi-leafless type that I showed you before, which is the main cultivated type, there is a certain correlation between pure stand yield and mixture yield, but not like a correlation that is by any means close to 1. So there are differences, different performances of the genotypes, whether grown in mixture or in pure stand, which is been shown here, and is an indication that breeding for mixed cropping might be interesting. I've also had genetic effects of all the different cultivars, which is not so much surprising, but like on GMA producer effect, with green symbols indicating a positive effect on the relative parameter, also land equivalent ratio. And well, this is not so interesting. Let's better look into this. So here I've plotted the this is all P cultivars. So every dot represents a P cultivar, one of the 28. And the solid dots and the non-solid dots, they are these cultivar mixtures. So these are 28 plus 4 dots. And here on the x-axis is the associate effect of P on barley yield. And here is the producer effect of P on its own yield. And you see a negative correlation between the two. Like the more the higher the barley yield, the lower the P yield, and vice versa. But this line here, this is not the regression line, but it's just like the intersection between these four quadrants. And so everything, sorry for people who are colorblind, so this is green and this is red, and green means that everything that is above this line has a positive GMA, either due to a high associate effect or due to a high producer effect. Everything that is below has a negative general mixing ability. And what you can see here, I think you cannot see the different colors so well, can you? So this is green. These are green dots here. These are medium types. And blue, these are blue dots here. These are short P types. And like these brown ones here, these are long types. You have long types, medium long types, and short types. And you see that there's like the short types, there the majority is below this line. So the majority of the short types has a negative general mixing ability. That's interesting to look at, especially if you look into these different traits and color them in this way. So, but what I found also is that if you take now these 28 P cultivars and we plot it a bit differently, for instance, the producer effect of P on its own yield on the x-axis and the general mixing ability, we see a clear positive correlation. So the higher the P yield, the more productive a P in the mix stand is on its own with its own yield, the better the general yield. So you would expect, oh, there must be a trade-off, right? So the more egoistic, so to say, the P is, barley must suffer from it, right? But this is not the case. So because here I've put the associate effect, producer effect, associate effect of P on barley yield, and again, general mixing ability, and there's no negative correlation. And the interesting thing is that this is the same thing is the case also for barley. So for if we were to look at the 7 barley cultivars, we would see the same pattern. Barleys that produce well under mixed conditions don't have necessarily a negative effect on P in mixture. And this has interesting implications. I'll touch upon this later. I also had a look, of course, on how my cultivar mixtures performed. How about time, Booker? Should I hurry up? Okay, thank you. I also had a look at the cultivar mixtures. So here, what you see on this picture, it's basically the same picture that I showed you before, just without colors. But you still see these solid black dots, and these are the actual yields of these cultivar mixtures. And I contrasted them with their expected yield. So let's say if a cultivar mixture contained 5 cultivars, I created the arithmetic mean of their performance of their components and plotted it here. And I compared it with these arrows to their actual performance to see like how does it shift in this matrix. So I had one mixture that only contained leafy genotypes. I had another mixture that supposedly only contained long genotypes. I learned later that this was wrong. It was a wild mixture of basically everything because I relied on what breeders told me if it's long or short genotypes, but it turned out it was short and long and everything. And these are all semi-leafless, and these are all short genotypes. And what you see here is that cultivar mixture long performed significantly better than its expected mean. And I'll discuss this later, so why I think that is. I also had a look at this biological interaction functions and the different traits. So what you can see here are 4 different traits. This is early vigor. It's very tiny. Sorry, I will read it out for you. So on top, first row, this is the early vigor scores on the x-axis ranging from 1 to 9. Then we have on the second row onset of flowering. This is the days after January 1st. Then on the third row, we have biomass score from 1 to 9 on the x-axis. And on the last row, we have stipule length ranging from around 30 to 70 millimeters. This is basically the picture that Peter already has shown you in the previous talk. So on the other hand, what we see on the columns, like the first column on the y-axis, you always see the GMA, like again, total mixture yield, then P yield, barley yield, and pure stand yield on the 4th row. So what's interesting here is that for certain traits, we see a positive correlation with or at least a correlation with the trait value and the general mixing ability, which might indicate that these traits play a role in mixture performance, and we can use them as readers to select upon these traits to improve mixture performance. For instance, we see here this positive correlation between stipule length and total mixture yield. In some cases, we have no correlation, like here for biomass, and we see here that the higher the biomass, the higher the P yield, but the lower the barley yield. So we have here a clearly antagonistic relationship of this trait, like competition, basically. Next, so I want to discuss all of these results now. And first of all, if we have a look again at these cultivar mixtures, and one was outstanding, which was this cultivar mixture long. And it was actually morphologically more diverse than I thought for 2 putative key traits, which was plant length and leafiness. So it contained leafy and semi-leafless genotypes, but it also contained short and long genotypes. Again, I relied on what the breeders told me when I ordered the trial seeds, and some breeder classifies his or her cultivar as a small one, where in reality it's rather tall, and vice versa. So that's all I could have in designing my experiment, and I ended up with a very diverse mixture actually for plant length, and this performed very well and above expectation. And I think it's due to the lodging resistance of the smaller P genotypes that longer genotypes could unfold their full potential in terms of leaf area, index, because otherwise they would lodge and everything would fall upon each other. And I think they could, the long ones profited from the lodging resistance of the small ones. And it's also interesting as a starting point for assembly rules, like how would you have to assemble these blends to optimize your mixture yield. So this would be a next research project maybe. And an improved cultivar mixture long could be a starting point for a mixture that could maybe even be higher in this graph. Then I had this effect of what I told you before, that producer effect was positively correlated with overall yield, but the associated effect was not correlated with overall yield. So there doesn't seem to be a trade-off between a well-performing P cultivar in the mixture and putting together a well-performing P cultivar in a mixture with a well-performing barley cultivar in the mixture. And if you remember, on Tuesday, we had this discussion with Maria Fink also, where she said, like, the basic, the limiting factor for higher yields in agroforestry is genetic diversity. And she said, like, they found out that there is, in their composite crosses, there's not necessarily a trade-off, but the plants, yes, they became more competitive above ground, in their project, but they also developed larger root systems. So what happens in pure stand condition doesn't necessarily always translate to what happens in mixture conditions, because in the mixture condition, plants explore different ecological niches. They're not identical, and they can profit from the niche space more efficiently than if everything is the same. And I think this is also what happens in this mixed stand condition. And this is very interesting because it opens the way to actually breed for mixed cropping. So it opens the way to say that at least until we reach a real trade-off, there is still possibility to develop pea and barley genotypes that improve overall genetic yield without having a negative effect on each other. And this is a bit contradicting the theories of the colleague of Roberta, Paolo Aniciarico, who claimed that actually a species that is in competitive disadvantage in a mixture this species needs to be made more competitive. Actually, what I saw is both of them can be made, let's not call it competitive, but can be made more productive. So there's no trade-off. And yes, what do I have here? I think so. When it comes to actual breeding, based on my results, a very simple breeding scheme that I would suggest for this case study would be basically a dual use breeding scheme, where you start off selecting for pure stand performance until F4 at the 4th generation, because it's very simple to select. You don't have to grow the plants in the plant community. You just select on performance. And there is a certain correlation with mixture performance, as we saw. And then, because mixture testing under mixed conditions is more laborious, you split it up, you take the best performing pure stand cultivars and test them under mixed condition. Okay, this is everything from my part, so I'm sure there are a lot of questions.